We talk about the Poisson distribution. So a random variable x will have a Poisson distribution with parameter lambda, where lambda is some positive number. If it can take, it's a random variable that can take values in the integers, 0, 1, 2, etc., and has the following masses. The probability that x is k is given by 1 over k factorial lambda to the k e to the minus lambda. Okay, so let's check that this is an actual probability. We need to take the sum. K goes from 0 to infinity. I didn't say here for which values of k, but any value of k, 0, 1, 2, 3, etc. So we need to check that the sum is equal to 1. Okay, so first of all, e to the minus lambda does not depend on k, so that comes out in front. And then this one may recognize as being the Taylor series expansion for the exponential. So this is e to the lambda, right? So this is equal to e to the lambda, and e to the minus lambda is, this is e to the 0, which is 1. Okay, so we have that. Now, what about the expectation? Well, for the expectation, we need to sum from 0 to infinity k times the probability that x is k. So in our situation, we need to sum from 0 to infinity k times 1 over k factorial lambda to the k e to the minus lambda. So again, there's a simplification here. K factorial is k times k minus 1, etc. So we can cancel k out. And also, before we do that, notice that here we don't have to start at 0. We can start at 1. Right? So start at 1, because when k is 0, this term is 0. So we get k minus 1 factorial lambda to the k e to the minus lambda. So now let me try to factor out some things. E to the minus lambda can come out, and also one of these lambdas can come out. So let me just take those out. So I'm going to get lambda e to the minus lambda times the sum from 1 to infinity k minus 1 factorial lambda to the k minus 1. So now I'm going to just change variables, right? So I'm going to let j be k minus 1. So now if k is 1, j is 0 to infinity, 1 over j factorial lambda to the j. Okay, but this is e to the lambda again, so that cancels, so we get lambda. So the expectation of the Poisson distribution is just lambda. That's the parameter. Okay. Now, the Poisson distribution is connected to the binomial distribution. Suppose that I have a sequence here of binomial random variables, NP. and where p is actually a function of n. So as n goes to infinity, p will go to 0, and assume that the expectation of these random variables, which is n times p, is constant equal to lambda as n tends to infinity. So we take a bunch of binomial distributions and then we fix the expectation and let n go to infinity, and p will go to 0 accordingly. Now I claim that for a fixed k equals 0, 1, 2, the probability that xn is k, the binomial distribution, converges as n tends to infinity to the probability that x is k, where x is Poisson. There's a convergence. Okay, so let's try to check that. Okay, let's start with the left-hand side. Probability that xn is k is n choose k, p to the k, 1 minus p to the n minus k, right? But what is p? P is given by this formula here. It's lambda over n. So I can substitute lambda to the k, n to the k, 1 minus lambda over n to the n minus k. And if we write down the binomial coefficient, and I'm going to write it like this, as n factorial over k factorial n minus k factorial. And remember, there's another way of writing this, right? Just let's write it like this, as n times n minus 1 all the way to n minus k plus 1, right? Over k factorial, but I'm going to switch n to the k under here and put the k factorial under the lambda. Okay. Okay, I just swapped the n to the k and the k factorial. Now, there are k terms here, and there are k terms in the denominator, so I'm going to pair them up. N over n, n minus 1 over n, n minus k plus 1 over n. So this will become 1 minus 1 over n, right, because the n cancel the n there, all the way to 1 minus k minus 1 over n. And now let me split up this as 1 minus lambda over n to the n, and 1 minus lambda over n to the minus k. Okay, I think we are ready to let n go to infinity. Remember, k is fixed. Now, that's really important. K is fixed. As n goes to infinity, this term here tends to 1. And this term tends to 1. So there are k minus 1 terms. They all tend to 1. Now, lambda k factorial doesn't depend on n. Here, this also tends to 1, because k is fixed, and lambda over n goes to 0. Now, what about this term here? 1 minus lambda over n to the n. This, I claim, tends to e to the minus lambda. So that in the end, we do get lambda to the k, k factorial e to the minus. We get exactly this expression here. Right? So why is 1 minus lambda over n to the n tending to e to the minus lambda. Well, let's take the e to the log, right? These are inverse of each other. So let's take e to the log 1 minus lambda over n. And remember, what does the logarithm look like? The logarithm function goes through 1 with a tangent of 1, right? Does this. So this is log x, the log. And so near 1, the tangent approximation, this is roughly the same as e to the n times minus lambda over n, which is exactly e to the minus lambda. Okay, so that's a proof of this limit. The binomial distribution for n large and constant average converges to the Poisson distribution.